Greetings and welcome to Flanigan's Ecologic. I am your host, Ted Flanigan, and today my guest is Hugh Broadhurst. He's the Chief Operating Officer of Aclara Resources. He began working for Aclara just about a year ago, June of 2025, and he's had a career in specialty minerals from agriculture and now renewable energy projects, minerals for those in those sectors. Today we'll be getting a primer on rare earth minerals and their importance to sustainability. Welcome to the podcast.
Great. Thanks, Ted. Great to be here.
And let's just a couple easy questions. Are you in Reno, Nevada as we speak?
No, I'm normally based in Reno, Nevada, but
Yeah.
today I'm in Belo Horizonte, Brazil, and I'm in our engineer's office, Hatch. We're finishing up a feasibility study for our big project here in Brazil, which is going to be a flagship heavy rare earth element project.
Oh, how fantastic. It's great. I've had people from all over the world on the podcast, and I would never have guessed you were in Brazil. So here we go. And well, you've already told me what you're working on this week. Can we spend a little bit of time? I mentioned in the intro there as a primer. What are rare earth minerals?
Yes, that's a great question, and it's one that gets used a lot with a lot of people not really understanding. So
Yeah.
if we think of the periodic table,
Yep.
we have a row of lanthanides and actinides, and there are a few other we lump into the term rare earth elements, but essentially it's 17 elements on the periodic table are considered rare earths. Every single one of them is different. It has a different use, a different application. That means there's a different demand, there's different quality requirements and different price points. And Aclara is focused on two of them in particular, and you can see them on my background. Dysprosium and terbium are the two critical ones that we're focused on. But then we also have many others that we'll be producing, but those are the two key.
So that really helps. And I was in my preparation for this podcast, I opened up the periodic table, which I hadn't looked at it in a while, to tell you the truth. So you've got these 17 elements that are sort of the building blocks for the rare earth minerals, right?
Correct.
Okay. And then your job is, as the Chief Operating Officer of Aclara, is to find where these minerals are found, and then to develop their extraction, and then I guess the downstream, I'm getting ahead of myself here, but the downstream activity is refining those minerals and pulling out the elements that you're after.
Absolutely. So we're focused on a very special segment of rare earth elements. They're called heavy rare earths, and I can tell you a little bit about why they're so important.
Yeah.
Because, and I'll use an EV as an example, as I think it's something we can all relate to really well. Now, when you get in an EV and you hit the accelerator, it's just incredible that torque that you get. You know, feel the seat pressing against you as you just get amazing acceleration. And the reason is you have your lithium-ion battery, and we have motors on the car that accelerate really quickly. But to get these motors to work, to get that torque, we have to use very high intensity magnets, or rare earth magnets as they're called. But there's an issue in that the main two elements used to make them, they're fairly easy to get hold of. But the issue is if you use neodymium and praseodymium, NdPr, their names are a bit of a mouthful. If you make an NdPr magnet at around 100 degrees Celsius, it's actually going to lose its magnetism. And we're putting so much power through these motors, they operate more around 150 degrees Celsius, so around 300 plus Fahrenheit. So they operate really hot, but the problem is with regular rare earths, the easy ones to get, they can't operate at that temperature. So what you do is you put 2 to 3%, the ranges vary depending on the magnet, of dysprosium and terbium into that magnet formulation. And what that does, it gives you the temperature resilience so that they can operate at the in-use temperature. Now, it's a really small amount of material. If you look at an EV, it's only about $50 worth of
Really?
dysprosium and terbium in that car. But without
Huh.
it, it can't operate. So when you see in the news that there are supply restrictions being placed on rare earths, it's not all rare earths. It's dysprosium and terbium, because for only $50 of in-use cost, the whole EV supply chain can be shut down. So that's the problem that Aclara is looking at solving.
Really interesting. Let me unpack a few things. And you talked about the formulation of the, I guess, the creating the magnet.
Yes.
What are the other? Or is it iron ore? Is it at the
Yeah,
core of the magnet?
there's iron, boron, and rare earths. I'm more focused on the production of the rare earths as opposed
Yeah.
to the magnet itself. But yeah, exactly. Just think of it as an alloy.
Yes. And the company Aclara has been described as a mine to magnet company. Is that
Absolutely. And I
is
can
that
tell you why. Absolutely. So we have two projects in South America we're developing. And when you look at rare earths, you can't lump all resource types, or let's just say deposits, into one category. They're all different. And there's one very special class of deposit, and it's called an ionic clay. And these ionic clays, so they are very rare. And outside of China, there's only really three ionic clay projects that are really close to operation. And Aclara has two of them. And so in Chile, we have one, and then one other in Brazil, which I'm working on today. And so ionic clays, what makes them special is that I can mine this material that's at surface. I don't have to do blasting. You can do it in a very environmentally friendly way. And Aclara's developed a process to extract the rare earths where all we do is wash the clay with a very dilute fertilizer solution. It's ammonium sulfate, regular material like in Miracle Grow that we all use in our gardens. And then from that, it's like a water softener. If you've ever regenerated a water softener at a house, it's exactly the same concept. Instead of using salt solution to regenerate it, we use ammonium sulfate, and that releases the rare earths from the clay. We then capture these, and then we have a very special water treatment plant that recovers 99% of that ammonium sulfate. So it goes in circles,
Yeah.
recycles, almost all of it. We recover 95% of our water this way. And it's a reverse osmosis treatment system making purified water. And we use that purified water to wash the clay so that we can put it straight back on the ground when we're finished, meeting all environmental regulations. So it's just a very sustainable process that we're incredibly proud of. But it's really the key to unlock the supply chain and do it in a way that people have come to expect things to be done today.
Yeah. How very interesting. Now I'm going to ask you a lot of naive questions because this is something I just don't know anything about. But this NdPr, I'm not even going to try to say what that means. But those are the two rare earths that you are providing, or that you are mining and refining to be able to
Yeah.
sell.
So
And does that
when
come
we
out? Oh, go ahead.
so when we take the clay, essentially and we wash it with the ammonium sulfate solution,
Yeah.
we get a whole mixture of rare earths. So we get our two target molecules, which are dysprosium and terbium.
Yeah.
We get NdPr, we get samarium, we get yttrium, gadolinium, you get a combination of these 17 that I told you about, because it's a natural feed. And what we do is we take that concentrate and we bring it to our separation facility. So that's our third project that we're working on. And this concentrate, so it's very, very pure, but it's a mixture. And one of the big challenges in our industry is there's not a lot of know-how and knowledge on how to make this separation. So we just inaugurated 2 weeks ago a pilot plant facility at Virginia Tech University, and we're making that separation there. And to validate our process. And once that's complete, we're building a separation facility in Louisiana where we'll make that separation. That produces rare earth oxides, highly pure, in the individual element, with the individual elements.
And
We then have
what form are those oxides? Are they a solid, a liquid at that
it's
point?
powder, a powder.
It's a powder.
It's just a
Okay, but you
powder.
said so you take it. So in that deposit that you have down in Brazil, you have all these 17 elements, and then you're separating them all out, and you've got these various powders that you sell into different marketplaces.
Exactly. And then we even take it a step further. What really makes Aclara unique is we have a vertical integration strategy.
Hmm.
And so what we do is some customers want those rare earth oxide powders, others want rare earth metals, so the dysprosium and terbium metal, and then other customers will want alloys. They actually want a precursor for the magnet making that's part of the alloy mixture. So what we're doing, we're vertically integrating, and that's why I said we have 4 different projects. We have 2 mines, a separation facility, and a metals and alloys plant that we're developing.
How very interesting. And you're doing this right now in Brazil, right?
So one of our mines is in Brazil. It's about 5.5 hours drive from Brasilia, the capital,
Yeah.
in the state of Goiás. And then we also have a project in Penco, Chile. And then both of these projects will make a concentrate. So our deposit, as I said, it's an ionic clay. You throw about 1,000 tons of clay, you get 1 ton of concentrate, this very pure but mixed concentrate.
Yeah.
And then we send that mixture from both of those 2 mines to our separation facility in Louisiana.
How interesting. Now, as I did a little bit of research, it sounds like, and you're going to help me out here, over 90% of rare earth minerals are in China. Is that right?
Yes, but it's even more abrupt when you look at dysprosium and terbium. Over 99% of dysprosium and terbium, these key molecules that can shut down EV supply chains, over 99% is processed in China today.
And is that, well, you said process. But
Processed.
does that also mean it's found there, or is it over
Yes,
90% is found there, but over 99% is
yeah,
processed there?
yeah. Well, what it is the Chinese are also mining in Myanmar, and
Hmm.
so the processing plants, they're located in China, but they're being fed from Myanmar as well as from China itself.
So you're not a competitor with the Chinese, or are you just an alternative supply from
Yeah,
the
we like
Chinese
to look
supply?
at great question, and we like to look at ourselves as an alternative.
Yeah.
When we bring, Clara, it means clarity, and what we do is to the Western automotive OEMs, we're bringing a product that is traceable. You know where it comes from, top quality, and something that we can all stand behind. And in today's world, it's not just what you produce, how you produce it matters. And
Right.
so we really take sustainability very seriously. And we're very, very proud of the way that we're doing our work.
Yeah. Let's talk a little bit more about other locations where these minerals are found. China is number one. I read Vietnam. Obviously, you're Brazil. You mentioned Chile. You mentioned Myanmar. Do we have these minerals in the United States?
Yeah, so it's a great question because there are rare earth minerals in the United States. There's a very big mine about an hour outside of Las Vegas. But this is a hard rock mine, not an ionic clay.
Hmm.
And what's very important when you look at that EV magnet, you have to look at what's the ratio. We call them light rare earths. So that's the NdPr. And when I say light, I'm talking molecular weight, where it is on the periodic table, or heavy rare earths, dysprosium and terbium. If you look in a magnet, it's about 15 lights to 1 heavy. Our deposits are 7 lights to 1 heavy. So that means we are helping supply more heavy rare earths to the market. Most mines, so the mines in, as I mentioned, in the US, also mines in Australia, they're all focused on the light rare earths, the NdPr. So we're missing, as an overall industry, we're missing supply of that of the DyTb, which, as I said, 99% over 99% processed in China. And so that's really what Aclara is focused on. We're focused on ionic clays because we can process them sustainably, and these two really key materials. And again, that's why I say all rare earths, they're different. You have to get past the term rare earth and look at the individual molecules.
Right. And I heard there was 160 known rare earth minerals out there.
Yeah, and for me, it's the 17 elements that
It's the
matters the
elements.
most.
Yeah.
Exactly. You focus on the elements and then the different deposit types, and each of them have their pros and cons and different ratios of the different elements that you're producing. So
And
it's
can
actually a
you,
really complex world that we simplify down to simple terms, but it makes it more complicated to understand.
right, right. And then are you able to produce these elements for a cost that's less than the Chinese can, or how does it work out in terms of pricing?
Well, and I think certainly our operating cost, we're not going to be able to compete directly with the Chinese. We really are approaching their operating costs. In China, how they mine these deposits is called in situ mining, where the ammonium sulfate solution that I told you about, it's just injected into the ground at the top of the hill.
Hmm.
And at the bottom, you collect the solution from the ground. So there's a lot of environmental contamination. We're
Hmm.
actually mining the material, so we have an additional cost of mining. However, as I mentioned, our reagent, we recycle 99%, whereas if you do in situ mining, you lose a huge percentage of it and your efficiency is less.
Yep.
So OpEx, perhaps we're slightly higher, but balanced. Where the challenge comes is to, and this isn't just rare earths. My previous work was in the lithium industry, and it's the same. If you want to produce things in a manner that the world expects, it does. We know how to do it. It does cost more,
Yep.
and so that's the constant challenge.
Gotcha. Let's talk a little bit about all the uses. You mentioned magnets, and
Yeah.
the magnets that are very important in the motors of electric vehicles. I know that magnets are also in motors in wind turbines. What are some of the other sort of sustainability related uses for these rare earth elements?
Absolutely. Great question. So wherever you think of electricity going to movement, you're going to need magnets. And
Mm,
whenever you're doing high torque or a lot of power, that's where you need the dysprosium and terbium. But so think of wind turbines. The wind turbines used to have gearboxes in them. They're now direct drive, and there's a lot of torque there. And so you're using rare earth magnets. Drones,
mm,
all the drones that, yeah, and I'm talking just simple drones that you can buy, for home use, have rare earth magnets. Also robotics, you name it.
interesting. And uh, how about in the household? I mean, you mentioned, even drones for homeowners who are almost hobbyists of drones. But where else do we find the use of rare earth elements in our homes?
I mean, the big one is going to be EVs, and the thing is, anywhere there's a magnet, there are small amounts of rare earth. Just almost any magnet has the high intensity magnets that we use today have some rare earths. Um, so the use, like if you look even in a car, just the rare earths in the steering wheel, there's the electronic steering wheel they use now. You just can't imagine. They're everywhere in very small amounts.
How interesting. Military applications. We probably had some crossover here, but in the discussion. But how are rare earths important for military operations?
Essentially, it's exactly the same thing. It's magnets. And
Hmm.
so whether submarines are electric powered, so that electricity has to get to movement through magnets. Also in airplanes, high temperature applications, they start to need some samarium there. But then also in supercomputing, actually,
Oh, really?
there's gadolinium used as well. I'm not an expert on the application side. I'm more of the
Yeah.
operation processing guy, but that's an idea of kind of where they're used. But all you have to think of magnets, and think of, especially where you have high intensity magnets and any power transfer, you're going to need rare earths.
Right. Right. And what would you say is the biggest challenge that you face at Aclara in as you said, from mining to separation to the
Yeah,
processing of
well,
all the
and
alloys?
it's a great question. The two sides of it. One is technical. Obviously, we're developing this whole technology. It has 99% processed, in China today, and now we're developing this supply chain. So there's not a lot of knowledge, but we're developing that. That's why we partnered with Virginia Tech.
Mhm.
We're working with our own national lab, and we have various consultants who've been working in this space. So there's the technical aspects, but the big challenge that industries have, and this isn't rare earths itself, it's really critical minerals. When you're trying to develop a brand new supply chain to the standard that the Western world wants, it's expensive. So the capital cost of these projects is high. And so as a startup company, where we have to develop the technology, prove we can do it, and then work on financing the project.
I'm glad you brought up the critical minerals because back to the primer here that we want to sort of get through. There's a difference between rare earth minerals and critical minerals. And I guess critical minerals are those with what they say strategic or an economic importance, um, might contain one or more rare earth. Is that right? Or what would you say is the distinction, Hugh?
No, absolutely. So Department of Energy and the U.S. Geologic Service has classified a set of minerals and let's just say elements, a set
Okay.
of elements that are critical to the supply chain security that we need for our country, for our economy, and progress. So this is a list that's been defined, and you can look it up. And this is what defines critical minerals. So there are things. Think of lithium, for example. That was, as I mentioned, that's the prior project I was working on. Lithium is considered a critical mineral. Dysprosium and terbium are also considered critical minerals. Samarium is considered critical minerals. So what it
Mm,
is that
mm.
we have 17 rare earths, 17 rare earth elements, and some of these elements are critical minerals, have been designated as critical minerals, but not all of them. So that's why we get confused
Right.
between
Yes.
the
Yes.
terms.
And how many, approximately how many critical minerals are there on that U.S. Department of Energy
It,
list?
it's now it's quite a substantial list, but it's different, and the different categories as well. Some are deemed to have a greater impact on the economy than others, and so minerals like dysprosium and terbium are right at the top, near the top of the list, whereas some other, slightly more common, but no less in terms of economic impact, perhaps, are rated slightly lower in the list.
Hmm. Hmm. So now, when you were a little boy, I doubt you thought I am going to be developing rare earth minerals for for electric vehicles. How did you? What's your career path? I know you got a degree, and first off, you're from South Africa, or you were educated in South
Absolutely.
Africa?
Yes. Yeah, I'm from South Africa, and I'm from a family of educators. My father was a professor of electronic engineering, and my mother was a math teacher. And so I tell my wife that this engineering thing is a genetic disorder that I can't avoid. And then during high school, I had a teacher who was it was my chemistry teacher. I just found the subject very interesting. So
Yeah.
unlike the rest of my family that went electronic engineering, I went chemical engineering. And then I was fortunate enough to be sponsored to do my master's in the US. And that really was the start. I got my master's in chemical engineering. And I
Yeah.
started with a company called Roman Haas. It's now part of Dow Chemical. And I started in specialty chemicals. So things like very high purity silicon carbide for the semiconductor industry. And these were all synthetically generated. So now rare earths, they're actually just a specialty chemical still, but it has a natural feed now. So we have that variability to deal with. So it's kind of been a natural progression.
And then, was I right about agriculture? Was it
Yes, yeah, I worked in
Anuvia?
yeah. So I worked in the agrochemical and fertilizer space for a period. So again, a different kind of essentially a specialty chemical. We're very focused on purity, and it translates very well to lithium and rare earths because we're making these high purity materials.
Huh. So those would not be considered rare earth. Those would be
No,
considered specialty minerals.
specialty chemicals was what we were producing there.
And then you kind of got into the lithium movement,
Correct, correct.
which is relatively recent, isn't it? The use of
Very,
lithium.
yeah. Lithium's it's had its uses, but it's really since the dawn of EVs that the demand has really picked up.
Yeah.
And so and now it transitioned to grid scale storage. So the lithium ion battery is really driven lithium demand.
And you were at Lithium Americas Corporation for
Correct.
almost 5 years.
Correct.
What was your role there? Was it the same thing, going all the way from mining to
Yeah,
separation or
slightly
refining?
different. I was the general manager for the Thacker Pass project in northern Nevada, and I
Hmm.
took care of process development and technology for the company and operations readiness. So we developed a lithium from clay process, and quite similar to now I'm doing with Aclara rare earths from clay. So there's been a natural progression and learning.
How interesting. And at Aclara, you have a lot to do. Right? It sounds like you're developing new mines, you're developing these separation facilities, you're supporting the whole supply chain of all these rare earth elements, rare earth minerals. Uh, I take it Aclara is just in a significant growth phase.
Absolutely. It's a tremendously exciting stage. We're developing 4 projects in 3 different countries, and we're bringing an alternative supply chain to the world in a responsible manner. And our next task is going to be to get these financed and get into construction.
And I think I read that Aclara is traded on is it the Toronto Exchange?
Correct.
So is that a Canadian company?
Yeah, officially we're a Canadian company, but our history is interesting because we are, I would say, a spin-off out of a company in South America called Hochschild Mining. They're
Hmm.
one of the largest precious metals, so gold and silver miners in South America, and they're listed on the London Stock Exchange. And the uh, the company had a Minerals of the Future project back in 2018, 2019. And that's when Aclara was founded and spun out when they acquired the project in Chile that I was talking about.
Hmm.
And then it's history.
Yeah. You seem like just the right guy to explain this to the world. I really appreciate your clarity, and
No
it's highly technical. I think those genetic roots, or engineering genetic roots, are served you well.
problem.
I'm getting the impression that what you're most proud of with Aclara is that you are adhering to a very strict environmental basis. Is that right?
We're making a product to go into the energy revolution, right? And what's the point of doing this if we're not going to do it the right way and to the standards people expect? That's what people expect. And to be honest, that's a huge motivating factor for our employees. We want to be proud of not just of what we're making, we want to be proud of how we do it. And it's very, very motivating. And we want to bring this solution to the world, but do it the right way.
Fantastic. Hugh, thank you so much for educating me and our listeners and for what you do. It's been a real pleasure meeting you.
Great. Thank you so much, Ted.
That's it. Thanks for listening to Flanigan's EcoLogic. We'll see you next time.